I have posted two announcements. Project 1 is posted and it's due on February 10th, midnight. And today students will start and you will come and we will discuss project as well as some background concepts that need a little bit of understanding before you can properly understand the first two chapters in the module. Those are not necessarily operating system concepts. Those are principles of programming language concepts. It's not needed for exams, but if you understand them, then you will better understand the first two chapters. In the exams, you have the first two chapters, and I have listed the tentative book chapters that you need to read for the exam. Only the first two chapters. The exam will be on Monday, next Monday. You can have one cheat sheet, A4 size paper. You can write, type, I don't care, both sides. Just don't throw the sheets around. You can, the exam will be of 30 minutes duration. You will probably have one or two questions which need some explanation. This the first module doesn't have any analytical questions. So Later, for other modules, you might expect analytical questions, but in this module, you won't have any analytical questions. So mostly explanations. You have to provide some explanations to the answers and some multiple choice questions. So you won't need more than 30 minutes to finish the exam. Now, some example questions that you can get. What I will do, the best resource is to go to the chapter 1 and 2 exercise questions in the book. That's the best resource. Now, there are some questions that are listed in the homework questions. I don't think these two have, but let's not spend time there. I will discuss this in the recitation session today. What questions you can study to be better prepared for the exams. I'll discuss this in the recitation session today, and I will video record it and post it so that not everybody needs to come. So that is with respect to exams and projects. Now let's get on with the content that we are discussing, unless you have some questions for me.
Okay, so you don't have like homework 1 anytime soon, right?
Sorry?
Homework 1, that's not like due anytime soon.
No, the homeworks are not due. It's for you to prepare.
Okay.
Homework, you don't have to submit the homework. Now, solutions for homework, you first try to do them, and I'll post the solutions later. You have any questions?
I was just going to ask, which questions from the homework and the practice?
I will tell you in the recitation session today, and I will video record and post it. Oh, so with respect to the video recordings, I did not post them in the Blackboard, but you can access them. What you do is you go to videos for fall. Only one class is posted, but what you do is you go to the CAC 330 channel and you see all the videos are posted. Even for this semester they are posted. So that's how you can access it. I will post one of these videos in the folder, and then that will make it probably easier for you to access. But right now you can access them in this way. Just go to the fall, videos for fall. And there is one class that is posted. Go to that, go to the YouTube link, and go to the channel. All the videos are posted. So your video starts from here, 10th of January, and then 12th, then 17th, and now today is 22nd, but 19th video is being posted now. It's uploaded. Okay, so let's continue. We were discussing the difference between programs and processes, and we said that programs are just inactive files. You just write some C code, that is program. You can't really run it. You can do nothing with it except for reading, and you can just read it. But if you want to run a program, then what you need to do is you need to have a process. Process runs programs. The process is the sequence of steps that you take to convert an inactive program file into an active execution. That is a process. Now, a single process can run multiple programs. It can run 10 or 20, 30 programs. A single program can be run by multiple processes. Now, one process can also create other processes. But a program, which is a static file, that cannot create processes. A static file cannot create processes. So I made 3 or 4 sentences which are kind of jumbled up. And not jumbled up, they are kind of interrelated. Right? So the first statement is a program runs processes. Processes runs programs. Right? And a process can run multiple programs. That is one statement. The second statement is a single program can be run by multiple processes. So these multiple processes which run the same program, these programs run on different inputs. There are different instances of the same program. That can happen. Multiple processes running the same program. Now a process, let's say process is running, that process can create other processes. And these other processes can either choose to run the same program or some different program. Doesn't matter. So a process can create multiple processes, multiple other processes. But a program, which is a static file, if it is not part of a process yet, that program cannot create process. That program is inactive, cannot create process. So that is the subtle distinction between processes and programs. Programs are inactive, processes are active. So now let's understand how do we go from an inactive program to an active execution. How do we go there? And in what stage of the conversion from inactive program to an active execution, in what stage do we need to create a process in order to start execution? So let's discuss this. So when you see a static file, a program, you have written it in C or Java or whatever high-level language you need to convert it into assembly. That much we understand. Because computers don't understand C, they don't understand Java. They understand ones and zeros. Right? So you have an assembly level program that the processor can understand. So you have to go from high level language somehow to an assembly level language. So now when we ask that question, a lot of you say, okay, a compiler does it. Right? A compiler takes a high level language, program written in high level language, converts it into assembly. And I said at that time, well, not quite. Right? It goes a long way towards assembly level language, but not quite. So what does a compiler do? So if you look at the figure here, when you write some function, say you wrote that function x, right? And that is in one C file, let's say. And then you called a function y. That y is in a separate C file. And that function y is again calling x back. Now when you write code, you call two types of functions in general. So one type of function is, the function is written in the C file, or I'm taking the example of C language. Let's stick to that. It will be same for Java and others, but let's stick to C. So if you are taking C language, then there are two ways you can call functions or declare functions. One way is you take the function and you write it in that file. Whatever file you are using to write your code, you just define a new function and you write it there. You write the definition of the function there, definition as well as the body of the function. That is one way. The other way is you call some function which is not really written in that file that you are writing code in, but is written in somewhere else, library functions. So for example, math.h, and you are using the function mean, right? Function mean in math.h. You don't write the definition or the body of the function in your code. The definition and the body is written in somewhere else, in some library. You might not even see the body of the function because it's pre-compiled. Right? You may not even see it. But you still call that function. So these are two different ways, and a compiler handles these functions in two different ways. So let's focus on functions that are written on the file, or that are written in the file that you are writing code in. Right? So it's a part of the code that you are writing. So if you do that, then let's consider the task of a compiler. So compiler takes line by line, converts into assembly. Maybe one line of C code is 3 or 4 lines in assembly, right? And assembly means bits, because we have a table, which says that okay, every opcode is some hex value, every data point is some hex value, and we can just replace the opcodes with hex value and get bits. So we'll just focus on assembly, because once you go to assembly, it's very easy to convert to bits. I mean, it's a very difficult mental task, but it is mechanical. So if you just think about it, anybody can do it. You don't need intelligence, or a machine can also do it. Right? So we'll just go up to assembly. So now the thing is, you are taking line by line C code, and you are converting it to assembly. One line in C code might be 3 or 4 assemblies of the lines in the assembly of the language. Now the question comes is, how do you call functions? We discussed this, right? We discussed this maybe last class or the class before. Normal functions, not even system calls. How do you call functions? You upload or you push all the arguments in the stack, and then the opcode that you use to call or to run that function is call. That is the opcode. And then beside it, as an argument of call, what do you have? Yes? Somebody was answering?
The address of the first line of the function.
Yes, the address of the first line of the function, right? When you are compiling, do you have the address of the first line of the function? You don't, because you didn't even convert into bits. So you didn't even go to the stage where you put the function into the memory, right? So you don't even have the first line address of the first line. So how can I convert this into bits? No way. A compiler cannot do that. So what does it do instead? It gives up. It says that okay, no, I cannot convert this function. I cannot convert this line into bits. So I put a tag. Right? I put a tag. I say that okay, this is some code that I cannot convert. Somebody else has to do it. Those kind of tags are called relative references. Those are relative references. So in that call line where you call that function, you go there and say that okay, there is a function call. It's a relative reference. Relative reference means that function is somewhere in that file. I don't know yet where it is, but it's somewhere in that file, right? And then you go ahead and convert the rest of it into binary. But that relative reference stays there, and a computer or a processor cannot read that, cannot make sense of that relative reference. It cannot. Doesn't know what to do. Right? So you cannot run that. You cannot run a compiled code. You need something else. That is one problem. The other problem is when you call library functions. When you call library functions, it's the same way you upload the input arguments and you have the call opcode and you have the address, right? That is even tougher. You don't know the, first of all, you don't know the address of the function that you just wrote in your code. How can you possibly know the address of the function that is not even written in the code? It's somewhere in some library. Right? How do you know that? You don't. Compilers don't. So, if this is a function which is a library function, you have to put a different type of tag. Because these two cases have to be tackled in a different way. Why? Because in the first case, the function is already there. So, after you have compiled, you know exactly where the function is. Yes, with respect to the file, not in memory. You don't know the exact memory location. But with respect to the first line of the file, you know exactly where the function is in the file. That's why you call it relative reference. Relative reference means relative to the first line of code in the file. But if you talk about library functions, you don't even know. If you have to follow some other path and let somebody search and find that function, compile it, or maybe if it's pre-compiled, you don't need to compile it. You take it and put it somewhere in your monolithic code, right? Because a computer cannot do all that conversion. A processor cannot do all that conversion. If you tell the processor, okay, go to that file location and run that code, it cannot. It only runs whatever is in program counter, right? It's in that sense very dumb. So you need a monolithic array of bits in order for the processor to be able to run it. So if you are trying to call a library function, somebody has to go to the location of that library function, make the binary of that library function, cut it or maybe copy it, paste it in your monolithic code that you have written, and then fix the addresses. Somebody has to do that. Compiler cannot. It cannot do that. So the references that you use to tag library functions, they are called symbolic references. So two types of references, relative references and symbolic references. These are all tags. So the output of a compiler is half binary, half tags. Now we won't say half, it's most of it is binary, but you have some tags in it. You cannot run it. Anybody knows what is it called? What is the output of a compiler called? It should be very familiar. Whoever is familiar with C. What do you do when you do GCC foo.c, and then at the end what do you write? -o, and then what is the file name that you give?
Whatever you want.
It should read, yes, whatever you want, but you should give it a name as some foo.o. Right? Yes, object file. So a compiler outputs object file. Object files cannot be run. Object files means it's a combination of binaries and tags, and these tags are relative references, symbolic references. Now in addition to the object file, you have two tables, right? And so these two tables are called relocation tables and symbol tables. Right? It's in the next slide. But we'll just look at this figure because it will make it more understandable. So in addition to the object file, you have two tables, relocation table and symbol table. Very simple idea. The table has the lines which needs fixes. Right? It's just the line numbers where you need to go and fix it. That is the relocation table. And the symbol table says, okay, how do I fix it? If it is a code that is written in the file, I don't need to do anything else. I already know the relative address. And if it is not a code, I need to know the path where I can go and convert the library function into binary and copy and paste it. That is what a symbol table is for. And relocation table says that, okay, which lines need modification. Now somebody has to take this object file and convert into something which is totally binary. Who does that? Linker. The linker does that. So what is the function of the linker? It uses the relocation table and the symbol table to go to those lines where it needs modification and modifies the addresses. Now the problem is, does the linker know exactly what memory address to put in there? Can the linker know? What? Yeah, no, it does not know. She says it has to be something that has to do with loader, right? But the loader is not there yet. We didn't run the loader. So the linker also doesn't know what address is. So what does the linker do? The linker considers that, okay, let's say the first line of code is address 0, the second line is address 1, third line is address 2, and so on. It starts giving addresses like that. These are relative addresses. Right? Then when it reaches that call function or tag, it reaches a tag. Now since you have given zeros and ones to all those 0, 1, 2, 3 to all those lines, if this function is written in your file, then that also will have the first line of that function will also have some number, right, related to the first line of code. It will have some number. So the linker takes that number and puts it into that line which needs fix. So instead of call some tag, you have call some 1200. That's some number. Remember, that's not memory address. Yes.
The symbol table that the linker has, is it the same as the symbolic table, or is it something different?
That's different. The symbolic table is used for proper execution, right? A runtime environment. So that is a table of variables and their what do you call it? Scope. Yes. So that is different. Symbolic table is different. This symbol table is different. So now, where are we? Yes. So the linker figures out the functions that are in the code, and just gets the relative addresses and updates the call tag that was there. Updates the tag with the relative address. It does the same thing for the functions that are not in the code. Whichever functions are in the library, it goes to that path. If it is precompiled, just copies and pastes it somewhere, maybe at the end. And if it is not compiled, it runs the compiler of that particular library and compiles it, right? And then copies and pastes it at the end. Now, if it copies and pastes it at the end, that also has a relative address. So it takes that relative address and puts it into the appropriate lines where you call. Right? So that is the function of the linker. Now what is the output of the linker? It's all binaries. No tags. Yes.
So how is it able to find the library function if it doesn't know the address of the code containing?
It has the file name, file address. So linker can go to that location and find out the file address locations. So now you have bits. There are no tags. You have bits which the computer can read. What is that output called? Yeah, what? What?
There is an extension for .bit corner with that.
No, not .bit, but you're close. It's called an executable, exe file. So after the linker, you generate the executable file. Can you run it? No. You cannot run it. You cannot run executable file yet. Why? Okay. You know executable file first line of address starts from 0. Compare two executable files and compare their addresses. They are the same. So in order to run an executable file, you need to put the address and put it into program counter, right? Now all the addresses start from 0 in executable file. So if you put an address and put it into the program counter, which program do you run? Right? One particular address is true for all programs, right? So you cannot run executables. So what do you have to run? What do you have to do in order to run executables? You have to run the loader. You run the loader. So what the loader does? Now the loader takes advantage of chapter 5 of this book, which is memory management. Right? And that is a different direction which we'll go to a little bit later. A lot later, not a little bit, lot later. Right? So we'll go to that branch lot later. But let's say it takes advantage of the memory manager. And how does it take advantage? Somehow the memory manager comes up with a memory address for the first line of code of that program. Somehow. How? Later. Right? So somehow it comes up with the first address. So that means if it comes up with the first address, then that means that from that first address onwards, we have the code in the memory. Right? All the subsequent lines are actual code. So now you have all the addresses. So the loader takes the executable file, puts it into the RAM, comes up with the first address. Can you run it? Not yet. Still not yet. So you have a program that is in memory. It has a first address. It has an address, actual physical address for the first line of code. But you still can't run it. Why can't you run it? Somebody has to take that first line of address and put it into program counter. Somebody has to do that. Who does that? Process. Resident monitor, yes, but the resident monitor how does the resident monitor do that? Creates a process. So that method of resident monitor taking the first line of address of the address of the first line of code of the function which is already in memory. That process of taking the first address of the first line of code, putting it into program counter, and many associated other things. That process is called, that sequence of steps is called a process. Right? So now, what other things you need to do? Now there are a lot of other things. Why? Because you have a program in memory. How do you know that is user mode, kernel mode? Right? How do you know that what is the stack pointer? How do you know what is the heap pointer? So you have to set all those things. That mechanism of setting up all those things and storing them in a particular data structure, that is called process. Now what data structure? This is very important. It's a very important data structure. And you have to remember the name. It's called process control block, PCB. Right? Process control block. And very similar idea is thread control block. Right? TCB. We'll talk about that a little bit later. It's a very parallel idea. I mean, it's almost the same, yet a little bit different. Right? And that we'll talk about when we talk about threads. But right now, let's consider only process control block. So, what does the process control block have? It's a data structure. We have discussed all this. Let's go to process control block. Oh, wait. Before we go to process control block, one item I missed. There's one item I missed. Now, the linker. When the linker outputs the executable file, we said that okay, there are some call opcodes, and as an argument to those call opcodes, we have relative addresses, right? And somebody has to change those relative addresses into physical addresses. If you don't change them, then the program execution sequence will all be messed up. So, in order to identify which lines have relative addresses that needs fix, the linker has something called relocation bits, right? So it is a huge monolithic code at this point. The output of the linker is a huge monolithic code with all bits, ones and zeros, and after every line there is one bit called the relocation bit. That relocation bit is 0 if you don't need to change anything there, and is 1 if you have to go there and change the address from relative to physical. So relocation bits. The loader, when it loads the entire code into memory, the loader makes use of the relocation bits. It goes to the lines where the relocation bit is 1 and takes the relative address, searches which one is the physical address corresponding to that relative address, and replaces it with the physical address. The loader does that. So the loader uses the relocation bits. Now after the loader has done that, then it's a code that is in memory that you can possibly run, but it's still not running yet. Then you need to create a process. After this point, after the loader, when the loader has used all the relocation bits, converted all the addresses from relative to physical, then you can possibly run it. Yes.
So the switch happens before the .exe is produced. The switch between the relative.
No, no, it's after, because loader is run after exe file is generated. Yeah. So loader is run on the exe file. So remember, so you might have seen that some file that is .exe and it's on the desktop, and you click it. So when you click it, the loader is invoked. Right? Because you can bypass all compiler and everything because it's already compiled, already linked. Right? When I double click on exe file, the loader is invoked. The loader takes all the zeros and ones in the relocation bit, converts the call addresses into physical addresses, and it puts it into memory. But the loader cannot run it. You need to create a process. So what the process does, it's a lot of management tasks that the process does. A process takes the address of the first line of code. Right? Now this process, you can tell the process to run multiple programs. In that case, it will have multiple addresses of first lines of codes of all the programs that it needs to run. So a process maintains a list of addresses of the first line of code that it needs to run. That is the first thing. The second thing is it keeps track of the stack pointer of all the programs that it needs to run. It keeps track of the heap pointers of all the programs it needs to run. It also can store the memory map of all the programs. Memory map means, so stack, there is some stack pointer and there is a base plus bound. Right? There is a base plus bound register beyond which a program cannot write. And there is a stack pointer. Now in between these two, a lot of changes have happened because the program has run. So that image of the memory, the process has to keep, has to store somewhere. Why does it have to store? Because remember, one of the major motivation of having operating system is that we need to stop programs from running for an infinitely long time. We need to stop them and let other programs run. So if we stop them, then somebody has to keep track of their status. Right? If we don't keep track of their status, then when we come back to the program, we have to run it from the beginning. We cannot afford that. We have to continue running a program from where we left off. So this memory map is very important, or memory image is very important. All that and much more. We'll see much more, we'll reveal them one by one when we go through all these chapters. But all that and much more is stored in a data structure called process control block. That is PCB. And if you have gotten a chance to look through your first project, you have to define one. There we call it thread control block because we cannot really work with processes. Why not? A very important issue. Why not? Because we are working in user mode. We are not working in kernel mode. Only in kernel mode you can create processes. You cannot create processes in user mode. You can create threads, but you cannot create processes. So that is a different issue that will come to that later. But that is process control block. So now when the process control block has all this information, the program counter and the status register has all that information of stack pointer, heap pointer, and it also has the mode bit. Right? If 0 is user mode, 1 is kernel mode, the status register has all that. Now the thing is, we said that okay, we give memory to the code and we are done. Loader does that, right? Loader just gives memory to the code. But we have to also give memory to the stack. We have to also give memory to the heap. And we have to give memory to the global data. So if we just give memory to the code, it won't run. You need memory for stack, you need memory for heap, and you need memory for global data. So whenever a loader calls the memory management unit, it doesn't just give memory to the code. It gives 4 different things. First, memory to the code, yes, which is deterministic. You exactly know how much memory you need for that code to store the code. Then second thing it gives is memory to the global data, again deterministic, because global data doesn't change during execution. But then it gives memory to stack and heap. These two are not deterministic. These change. The amount of memory required by a code is in stack and heap is changing. Right? So how does a memory management unit know how much to give to a particular program? Turns out it doesn't know. It just guesses. Yes.
Sorry, so is the memory management unit in the PCB or is it separate?
No, that's a separate unit, separate piece of software that is there in the resident monitor. or operating systems. PCB is just a data structure that stores all this information. The first line of code of all the programs, the status register, and the memory image. That is what PCB is for. But what I am discussing now is that in order to run a code, you just don't need just memory for that particular, to store the code in the memory is not sufficient. You have to have space for global data, stack and heap. Now stack and heap are varying during the execution of the code. So if they are varying, how does the operating system know how much to give it? Turns out it does not. So what does it do? It has a random guess. Say 4 MB. 4 MB stack plus 8. Why? Your choice. It's the choice of the operating system designer. If you need more, you have to call system call. You have to do a system call and increase your base plus bound. If you don't need it, well, it goes to waste. That is called internal fragmentation. This don't need to remember the term now, but later we will talk about this again. So yeah, forget about internal fragmentation right now. So you need memory for 4 things. You need stack, heap, code, and global data. Right? Now, once you have given this memory and you have created a PCB, so initially what will you have? Initially for the memory image, everything is empty, nothing there because the program hasn't yet run. Then you have to have a stack pointer, you have to have a heap pointer. All those are decided at the beginning. So heap pointer is typically at the right below the last address of the code, and stack pointer is at the end. So there's base plus bound becomes stack pointer. Right? So these two you have, you store it in the PCB, you store the mode bit, you say it's user mode, then so make it 0, and then you have the first line of address. Address of the first line of code. So you have made a PCB, now what do you do? You have made a PCB, what do you do now? You still cannot run it, yes?
So go one at a time?
Yes, you go one at a time, but how do you know where is that one at a time? You are right. His thinking is right. You go one at a time. So you have to have something to store things through which you can go through one at a time, and that is a queue. So the operating system is filled with queues, lot of queues, and that's why the first project is for you to design a queue. Right? Queue is very important in the operating system. You have a lot of queues because you have to go one at a time. Right? So what you do, what the process does, is that it takes the PCB, puts it into one queue called the ready queue. Right? It's called the ready queue. Then what happens? That is the end of the first few steps of the process. It then just waits. Waits for what? The CPU will now read the ready queue. Right? Take the PCB, unwrap it, take the first address of the first line of code, put it into program counter, take the status register, put it into status register, and run it. So that task, who takes the PCB and puts it into program counter and status register, that is done by the CPU scheduler. That's what we will talk about now. Right? That is the 4th chapter or 3rd chapter, I forgot, in the book. So we will talk about CPU scheduler now. But after discussing some more concepts, a little bit more concepts. So now the thing is, we already know about ready queue, right? We already know about ready queue, but there are several other queues. So first of all is init queue. What is init queue? Init queue is a set of all programs for which PCB has not been created yet. So that is called the init state. So you have started a process. You have just created a process, but the PCB is not finished. So it takes some time to generate the PCB and store it in the ready queue. Right? So that initial state where the PCB has not been created fully is called the init state of a process. So I just requested the resident monitor to create a process. That state is init state. Now once you have created a PCB creation is done, and you put the PCB into a ready queue, then that state of the process is called the ready state. So the process has several other states as well. So let's look at the state diagram of the process. So two states we know, init and ready. Init we know what? It's just the resident monitor or the operating system has gotten the signal that I have to create a process and has started creating the PCB. Hasn't finished yet. So that means that particular process is in the init state. Then let's say the PCB creation is done, PCB is put into a queue, ready queue. That state of the process is called the ready state. Now let's say you run the CPU scheduler. There is another piece of program in the operating system. Right? You run the CPU scheduler. Remember we had the driver, and then on top there were two things, scheduler and memory management unit. So we are talking about scheduler. We'll talk about MMU later. Right? So the scheduler is a part of the operating system, you run it. What does it do? It somehow decides which PCB to take from that ready queue. Somehow decides. Right? How does it decide? That is the entire chapter 4. That's what we will talk about. But for now, let's think that it somehow decides that I need to take some PCB, put it into what? Take the program counters, put it into program counter register, take the status register, put it in the status register of the CPU, and so on. So now when the CPU is actually running the code, because once you put the address into program counter, it runs. Right? So when it's running the code, then the process goes from ready state to run state. So which means that this is a process where one of the programs that the process is trying to run is getting CPU cycles. So that means you are in the run state. Now corresponding to run state there is a queue. Right? Because you have to take the PCB from the ready queue, pop it from the ready queue and put it into somewhere. So you put it into a run queue. Right? So run queue, since we are only focusing on a single processor system which can only run one process, the length of the run queue is 1. You can only have one item in the run queue. Right? So that's why we'll consider the run queue and the ready queue almost the same. But right now there is a difference. I mean, in concept there is a difference between ready queue and run queue. But since this is just a single processor system we are discussing, run queue always has one element. We can use them interchangeably, run queue or ready queue. Right. But for now, let's say that there is a separate run queue. Now, when you are running, several things can happen. Right. One thing that can happen is that you compute and then suddenly you need some data. Right. When you need some data as input, or you want to do some output, whenever you have to work with data, what do? You have to do system call. Right? You cannot, the user program cannot work with data. If you want to work with data, you have to do system call and ask the operating system. So then the operating system takes over. So what happens to your process? You just don't compute, you just wait. Right? So in that case, the process goes from run queue to a wait queue, which means it is doing input output. It's waiting for the operating system to give it a signal that okay, your input is ready, go read it. Or your output is ready, it has already printed, you can continue execution. It waits for the operating system to give it that signal. So it is in the wait queue, it's not computing. The CPU is free. Right? So that is one possibility. The other possibility is that it just ends. There is nothing more to do. Right? So if it has nothing more to do, then again this is another concept of programming languages that you need. You don't really need, but it's good to know that once it's done, it has to deallocate memory. Right? Deallocate memory. So that deallocation of memory, as well as deallocation of the PCB, because you have to remove the PCB, you have to free up space for the PCB and all that. kill the process, right? So that, all those things happen in another queue called the exit queue. Right? So and the process is said to be in the exit state. So we have learned about two possibilities. One is you do input output, you go to the wait queue. Another is you just ended and you go to the exit queue and you go out of the system. Now let's consider the wait queue again. So you have some input output data, you are in the wait queue. What happens when you are done reading? You don't come back to the run queue. You go back to the ready queue. And you wait for the CPU scheduler to take you back to the run queue. So you cannot immediately spring out from the wait queue and go back to the run queue and start processing. You have to wait for the CPU scheduler. And the CPU scheduler has to choose you in some time. And until that happens, you just wait in the ready queue. Okay. So we have seen two possibilities. There is one very interesting possibility, and that directly corresponds to the second motivation of our operating system, that we want to preempt processes. That is called preemption. Preempt processes means you are not done yet, but stop, let others go. Then when it's when they are done, we'll come back to you. So that is called preemption. Right? So when a process is in run state, it can be preempted. How do you preempt? Remember we talked about interrupts? Interrupts driven by clocks. And we said that okay, there might be a function where you can just switch the program counter. That function is called context switcher. So whenever you expire certain time, the context switcher is run, which switches the program counter. And the process from which you switch, that PCB goes back to the ready queue, and the process to which you switch, that PCB goes from the ready to the run queue. So the CPU scheduler, which we will talk about next, is somewhere running in between the run and the ready queue. So we'll continue from here next time. So today go to the destination because